What I have to do, what I choose to do today is to give you a quick introduction to the moment map. In GIT. So this is a Deus ex machina. So this is a sort of something from differential geometry, which seems to, on first sight, just quickly, I'll be back, Kavi, just 1 second. Yeah. Which comes out of differential geometry, which seems to be very important, in fact, which has proved to be a very, very important idea to understand GIT quotients over the complex numbers. So if I try to give you a detailed introduction to this, it'll be just way too much to take on board. So I will black box huge amounts of stuff. Okay. So, so let me quickly tell you roughly what the moment map is. So start with some linear algebra. So if V is a real vector space, and I'm given a map from V to V dual, linear map, its transpose is also a linear map from V to V dual. So if you call T transpose, and T is symmetric if T transpose is T, and skew symmetric if T transpose is minus T. So one way that, so supposing I'm given a symmetric map, you get a, both these give you bilinear forms on V. So given a map from V to V dual, there is an associated bilinear form. So on V, given two vectors U, V in V, this is TU evaluated on V. And if T is symmetric, BT is symmetric. The bilinear form is symmetric. And if it's skew symmetric, BT is skew symmetric. In fact, if you wish, you can take this as a definition of symmetry, symmetry or skew symmetry of a map from a vector space to its dual. So now, if M is a manifold, a Riemannian metric on M gives at every point P in M a symmetric bilinear form, the Riemannian metric, and therefore it gives you bilinear form TP, map TP from the tangent space at M. So T is a bad notation, a map from TPM to TPM dual. And this is symmetric. So this we are familiar with, but you can also give yourself a skew symmetric map from TP to TPM for every P. Imagine we have a skew symmetric map TPM to TPM dual for every P, then you get a corresponding bilinear form, which should be skew symmetric, which for tradition, I call it omega P UV, is I take U, apply this map, let me call this tau, and evaluate on V. Okay. So now, I can make the definition if I have, and so this will give me a skew symmetric 2 form on M. So if we have this at every P, at every P in M, we get what's called a skew symmetric or exterior 2 form. On M, and if 2 conditions are met, we call this a symplectic structure. What are the 2 conditions? One is that at every point, the map TPM to TPM dual given by omega should be an isomorphism. So that is a punctual condition, means it holds at point by point. And the other condition involves differentiation. This exterior 2 form should be closed. Its D exterior derivative should be closed. If both these conditions are met, we call this a symplectic structure. So the symplectic structure is a natural analog of a Riemannian, sort of skew analog of a Riemannian structure on a manifold. So on a manifold, if you are in the world of symmetric structures, the natural thing is to think of Riemannian metrics. And if you are in the world of skew symmetric structures, the natural thing is a symplectic structure. Now, the important thing to remember, I mean, there are many important things to remember, but both these structures enable us to start with a function on the manifold and get a vector field. So both a Riemannian structure and a symplectic structure enable you go from functions on M to vector fields on M. So take the space of vector fields on M, take the space of real valued functions, real valued, and always smooth, okay, C infinity functions to C infinity vector fields. So in the case of the Riemannian metric, so this is called the gradient. And in the case of, so Riemannian metric, and in the case of the symplectic structure, this is called the Hamiltonian vector field of F. How do you do this? You go from F to DF. This is a 1 form. And so that means for every P in M, DFP is an element of TPM dual. Now, on the other hand, I want a vector field is for every P in M, an element of VP in TPM. So here, note there's a dual here. So how do I go from the dual to the dual tangent space, dual in the tangent space to the tangent space? Well, use one of these structures. If I have a Riemannian metric, I can use the metric to identify the dual of the tangent space with the tangent space. So given an element of the dual of the tangent space, I get an element of the tangent space that is called grad f at P, that uses Riemannian metric. And if I use the symplectic structure, that's called the vector field, Hamiltonian vector field, which I will just call it Vf at P. Okay. Now, suppose we have a symplectic manifold and a group G, let me call it K for good reason, acts on X, preserving whatever that means, the symplectic form. Then we get, under mild conditions, a map X, sorry, M to the dual of the Lie algebra of K, K hat, dual of Lie algebra of K, which uses the symplectic structure in a way that I will describe. The map uses, using the symplectic structure, we get using the symplectic structure. Now, there are, this map has a defining property and one other property that follows from the defining property. Let me define, these are the two things I have to tell you. Defining property of M. And what is the other important property that follows from this? This is K equivariant. What does that mean? So remember, K, the group K acts here. K also acts on the dual of the Lie algebra because every group, Lie group, acts on its Lie algebra. This is the adjoint action. Therefore, the dual action on the dual vector space is natural. So K acts on both sides of this map. And the point is that the moment map is equivariant with respect to the action of the group on the two sides. Okay. Now, what is the defining property of M? Now this will be quite a mouthful, okay? But you have to remember everything that went before, okay? Okay, defining property of the moment map. Okay, so the moment map is this equivariant map from this symplectic manifold with a K action to the dual of the Lie algebra. Okay, what is the defining property? Let psi be any element of the Lie algebra of K. Now, when a group, Lie group, acts on a manifold, then you have the infinitesimal action of the group, which gives you, for every element of the Lie algebra of the group, a vector field on the manifold. So V psi, let V psi be the corresponding vector field on X. On the other hand, so far the moment map has not come into play. If I look at this map from X to, consider this map from X to R, X maps to Mx evaluated on psi. So Mx is an element of K star, psi is an element of K, small k. So I can evaluate this element of the dual of the Lie algebra on this element of the Lie algebra to get a real number. Okay. So as X varies, I get a function, real valued function on my symplectic manifold. Now remember, on a Riemannian manifold or on a symplectic manifold, that structure gives you a way of converting, going from functions to vector fields. So now we forget the Riemannian structure, we have a symplectic structure. So I can take the corresponding Hamiltonian vector field corresponding to this function. Okay, take this real valued function. I'm putting the dot here because X is a variable here. Take the real valued function got by evaluating the moment map on the Lie algebra element xi, and as the point of the manifold varies, you get a function on the manifold. Take the corresponding Hamiltonian vector field. This should be equal to the vector field given by the infinitesimal action of the original psi. Now, this is quite a contorted definition at first sight, and in fact at second sight, but it's a definition that really works. I should warn you that there are always sign conventions, and everywhere there are plus minus signs. This is a quicksand of signs. Okay. So the point is, when I have a group acting, Lie group acting on symplectic manifold by symplectic transformations, whatever that means, because I have not defined that properly, you get a very important and entirely natural map from the manifold into the dual, into this vector space. Remember, the manifold can be a complicated object with lots of topology and so on. And in fact, it's got this symplectic structure. But the Lie algebra is just a finite dimensional real vector space. And the dual is just the dual of that. The point is that you have this action of the Lie group on your manifold. You have the action of the same Lie group on the dual of the Lie algebra, and the moment map M is equivariant with respect to this action. So in other words, M evaluated on Gx at the point Gx is got by evaluating M at X, so which gives you a vector in the dual of the Lie algebra. Transform that vector by the linear transformation given by G, that gives you the result that you want. Okay, that is what equivariant means. So this is the ingredient. So now let us just get some intuition I'll give you some examples of moment maps. I will not verify that these are moment maps. Okay, but you kind of ask what else can it be, and that is, that works. Okay, so examples. So before I go to examples, because we don't have that much time, let us quickly specialize to the case at hand. So what are the symplectic manifolds that we are going to deal with? So we are going to, in fact, deal with a particularly felicitous conjunction of two different kinds of geometry. Namely, there is going to be symplectic geometry. In fact, three. There is going to be Riemannian geometry, and there is going to be holomorphicity. And these three come together in the case of complex projective varieties. So the point is that if V is a complex vector space, then choosing an inner product, complex inner product, Hermitian inner product, on B puts you in the following situation, gives you the following. One, V, W, R equals real part of V, W. This is, so this is the inner product, huh? On B is a real inner product on the underlying real vector space VR of V. In other words, if I take the complex vector space V and just forget to multiply by imaginary numbers, I get a real vector space of twice the real dimension, real dimension equal to twice the complex dimension. And if I take the Hermitian inner product, which is not a complex number, given two vectors V and W, the inner product is not a complex, it's not a real number. But if I take the real part of it, I get a real number. And in fact, this is a symmetric bilinear form, which also has the property that if I take V inner product V, that's strictly bigger than 0 unless V is 0. So this is a real inner product.
Okay. So the left-hand side is thinking of V and W as sitting in a real vector space, and the right-hand side is the... Okay.
Exactly. If you take V omega, let me call it this omega VW is imaginary VW. This is a skew symmetric form, which in fact gives an isomorphism VR to VR dual by that procedure, going from a bilinear form to a map to the dual. This map is actually an isomorphism. So, okay, this is all now. The point is you can now think of this as structure on the vector space, but now you have to kind of think of the vector space as a manifold, because I can just move this structure from point to point on the vector space in a natural way. The tangent space to the vector space at any point is canonically identified with the vector space itself. So I can just move this point structure from point to point on the vector space. So in fact, this defines a Riemannian metric, and this defines a symplectic form. Okay. And given the inner product, I have the corresponding unitary transformations of V, and unitary transformations will act as orthogonal transformations. Now, if you think of the unitary transformation of the complex vector space, it is also a linear transformation of the same vector space thought of as a real vector space. And if you think for a minute, you can see that in fact, a unitary transformation of a complex vector space with an complex inner product is actually an orthogonal transformation of the same vector space as a real vector space with the real part of the inner product. That is clear. But it also preserves the symplectic structure, the skew form. So all this is to say that UV acts on V by symplectic transformations. Okay, if you believe all that, you will believe that I should get a map M from V. It should be thought of as VR. So let me put VR, okay? Just so whenever you see VR, I'm thinking of this complex vector space as a real vector space of twice the dimension. So if you believe all the stories so far, there should be a map from the real vector space VR to the Lie algebra of UV. But what is the Lie algebra of UV? It is skew Hermitian maps V to V. Even though when you say skew Hermitian, there is all kinds of complex numbers there in the definition. Remember, skew Hermitian maps are only a real vector space. If I take a skew Hermitian map and multiply it by I, you actually get a Hermitian map. So the space of skew Hermitian maps of a complex inner product space is only a real vector space. Okay? And UV acts here by, as I said, preserving symplectic structures. And UV acts on skew Hermitian maps just by adjoint action. Therefore, it acts on the dual of that. So dual. So I forgot the dual here. The M should go from here to here. Okay. But now there is a natural pairing between skew Hermitian maps and the dual and between themselves given by a product. Take the product and take the trace. Okay, maybe after multiplying by I. So I can, without too much thought, I can just identify with, I can forget about this dual here. Okay, I'm really going very fast because I need to cover a lot of this thing. So there is a equivariant map from VR to skew Hermitian maps. Okay. Now, and what else can it be? I mean, so if you think for a, I will give you a very natural map, and you know, I will just declare that this is it. So what do you have to do? You are given a vector V in V, and I will give you a skew Hermitian map of V to V. Okay, so it's just this. Yeah, it goes to 0 if V is 0, and if V is not 0, it goes to take the projection onto the one-dimensional subspace spanned by V, okay, multiply by I, and multiply this by norm squared V. So if for the zero vector, the skew Hermitian map is just the zero map. If I have a non-zero vector, it gives you a one-dimensional subspace. Take the orthogonal projection to that that one-dimensional subspace. That's actually a Hermitian map. Multiply by I, so you get a skew Hermitian map, and multiply this by the norm squared of V. Okay, and this is in fact the moment map. Now hold that thought. Yeah, KV. I can't hear you. You're muted.
Sorry. So is there a basis in which one can see this easily, or I mean,
if you want to verify this, then one way would be to write it with a basis.
Okay.
I mean, but the point is,
so the way to think, so once again, you're saying take V, look at the projection onto this one-dimensional subspace.
The orthogonal projection.
Or the orthogonal projection. Orthogonal projection. Okay.
Because you have chosen an inner product.
Yes.
That is why you have a UV. The point is,
correct.
In a complex vector space, there is no UV. Once I choose an inner product, then the unitary transformations with respect to that inner product make sense.
Okay.
Okay. And you need the inner product also to define the symplectic structure. The inner product is, without the inner product, you only have algebraic geometry. The inner product brings in differential geometry and on the full machinery. Okay. The real inner product gives you a Riemannian metric by taking the real part of the inner product. It gives you a symplectic structure by taking the imaginary part of the inner product. It singles out in GLV the unitary transformation UV, which acts as orthogonal transformations for the real inner product and symplectic transformation for the imaginary part of the for the skew inner this thing.
Correct.
Therefore, now forgetting the Riemannian metric but concentrating on the symplectic structure, you will look for a moment map for this action. The moment map should be a UV equation. You remember the group in question now is UV.
Is UV.
So that's what GLV doesn't act symplectically. GLV doesn't preserve inner products.
Correct.
The subgroup of GLV that preserves inner products is UV.
Is UV. Correct.
Okay. Therefore, because it preserves the complex inner product, it preserves both the real part of this and the imaginary part of it. The imaginary part defines the skew form, the symplectic form. Therefore, by the general formalism moment map, I should get UV equivariant map from the vector space to the dual of the Lie algebra of UV, which is skew Hermitian, dual of skew Hermitian endomorphisms. But skew Hermitian endomorphisms dual can be identified with skew Hermitian endomorphism, something like a killing this thing. So I'm looking for a UV equivariant map from V to skew Hermitian endomorphisms. And up to this norm V squared, which is a real number, I mean, which is not a constant real number, it's a real function. It is just given a vector, it's just the length squared of that vector. This guy. This is just take the projection on, so take any non-zero vector, take the projection on that. Orthogonal projection is a Hermitian map. Take I times that, you get a skew Hermitian map, multiply by it. And everything is so natural that you don't even have to check equivariance. You are only using invariant structures to define the map. Because if the map is defined in terms of the inner product, it has no chance.
So orthogonal projections will be, so if I move it by U and then I project it,
if I conjugate the orthogonal projection, that will... Correct. So there's really nothing to check. Okay. Now let us consider the projective space of V. Now, again, I have GLV acting on this. And so this is the context in which we define PVSS and we define pi P to PVG, etc. Okay. But now let us see let's bring in the moment map formalism here. Now, again, K, which is a subgroup of GLV, will act on PV. But now PV is not a vector space, so I need to, there's no getting around it. I need to have a symplectic structure on it. And in fact, the there is not only a symplectic structure, there is a Riemannian metric, and the two are very tightly bound, and this is what's called a Kähler structure. In fact, on V also, the complex inner product gives you, what it's doing is actually giving you a very special kind of Kähler structure. It's a constant Kähler structure, which is the same independent of where you go on V. Okay, so that's what we started with. So the point is, there is a what's called a Kähler structure on this coming from the inner product on V. The inner product, choice of inner product on V determines this and determines the Kähler structure. And Kähler structure is Riemannian metric, symplectic structure. And these two are joined together in a complicated way by the complex structure, which I don't have time to go into. Okay, so now, so K acts on PV, preserving the symplectic structure, whatever it is. I have not defined it. But if you believe it exists, there will be a moment map from PV to again skew Hermitian endomorphisms of V. And the fantastic thing is, M at a point V is actually I times PV. So look at the difference between here and PV over, sorry. Okay, look at the difference between this formula and this formula. So this was for the vector space. So I had this, this factor here. Now for the projective space, I just dropped that factor. And so all I have to make sure is that the right-hand side doesn't depend on the representation. So remember, this notation is that V is a point of PV, and V hat is a vector, non-zero vector above V, right? So this square bracket stands for an equivalence class of non-zero vectors all lying on a one-dimensional subspace. So a point of PV is not a vector, it is a one-dimensional subspace. And what could be more beautiful than this? The moment map for the action of UV on PV is just the following. Take a point of PV, that is a one-dimensional subspace, take the orthogonal projection to that one-dimensional subspace and multiply by I. Okay. So now, but of course, this is typically we don't look for semistable points for GLV acting on PV. There are none. So you have to look at semistable points for subgroups of GLV acting on V. Okay. So what about subgroups? Of GLV. So here, what comes to a rescue is the fact that this moment map is a fairly functorial guy. Okay, so I see. I don't mean functorial. I'll call it functoriality of moment map. This doesn't mean functoriality in some grand categorical sense. I don't think. I could be wrong. So what is this? One, if X is a symplectic manifold, and I have a K acting, preserving symplectic structure. And Y is a subspace, submanifold, which is symplectic. That means that the restriction of the symplectic form from X to Y gives you a symplectic form on X, and K invariant. So Y is K invariant symplectic submanifold. My is equal to mx restricted to y. So if I have a Lie group acting symplectically on a bigger symplectic manifold, and it leaves a submanifold invariant, and the symplectic form restricts to symplectic form on the submanifold, then if I take the moment map for the bigger manifold and just restrict it to the smaller manifold, that's a moment map for the smaller manifold. Secondly, if K and K prime, so X, so I have this situation, symplectic. So I have a group, Lie group K, that acts symplectically on X, and a subgroup K prime. Now, if the bigger group acts symplectically, then clearly the smaller group will act symplectically. So I'll have a moment map M from X to K dual. On the other hand, I might want to look for a moment map
for K prime.
X X to K prime hat. How are these two related? Well, if K prime is a subgroup of K, the Lie algebra of K prime is contained in the Lie algebra of K. Therefore, if I take the dual of the Lie algebra of K, that will map surjectively to the dual of the Lie algebra of K prime. So if I take this and project by this surjection, I get M prime. So this is why it's, even though often you can use an invariant form to identify K with its dual, the Lie algebra with its dual, it's better not to do it because if the group in question is not compact, there may not be such an identification. But more to the point, this thing will become awkward if it's better to think of the moment map as mapping to the dual of a Lie algebra, because then this map, I mean, did you get this? This is an important point. Should I repeat it? Should I repeat it?
Yes.
Yeah. So if I have a Lie group acting on a symplectic manifold symplectically, preserving the symplectic form, and if I'm given the moment map for the Lie group K, which is, as I said, it's an equivariant map from X to the dual of Lie algebra of K, satisfying some conditions. And then if I want the moment map for a subgroup of K, it's got by looking at the map to K dual and just projecting from there to K prime dual, because the inclusion of K prime
gives you a map going there. Correct.
If you dualize, gives you a map going the other way.
Correct.
Okay. Okay. So once you the second thing is very relevant to us, because now if I now have I have V, I have V vector space on which some group G acts. Then if I choose inner product, choose inner product on V, that gives you maximal compact K. K will act symplectically on PV, and there will be a moment map M from PV to K dual. Okay, now I can come to the main theorem. PV SS modulo G is in bijection. Well, you can say much stronger things, but it's important just to start with this. Take M inverse of 0 modulo K. So by 0, I mean, let me just be explicit.
The 0 form, is it?
No, M inverse of 0 of K dual. So M is a map, equivariant map from PV into this vector space, the dual of the Lie algebra of K. Take the inverse image of 0. That would, because this map is K equivariant and 0 is fixed by K, K will act on the pre-image of 0.
Pre-image. Huh.
Okay.
Does it act freely on the pre-image, or it depends?
No. The point is, first of all, M inverse of 0 K prime
is a K mod.
Remember, M is actually it's even a C infinity map from PV to K hat. And the inverse image of 0 will be a closed set. So it'd be a closed set in a compact space. So M inverse of 0 K is compact. This guy. K is also compact. So you have a compact. You have a compact Lie group acting on a compact topological space. In fact, if in good cases, extremely good cases, this will be a free action on a manifold. Okay, so this realizes the GIT quotient as an as a quotient of a compact topological space by a compact Lie group. Okay. In good cases, this will be a free action on a manifold. So this guy will be the base of a principal K bundle, where the total space is just the M inverse of 0K. Okay. So this,
and in what sense is the bijection? When you say bijection?
Well, for example, in some good cases, when the right-hand side is a manifold, the left-hand side will be a manifold, and this will be a diffeomorphism. There will be a natural, this will be a diffeomorphism, and the left-hand side will come with a symplectic structure. The right-hand side will sometimes come with under some choices will come with a Kähler structure. Okay, so this will preserve all possible structures that can be preserved, depending on how good your situation is. Okay. Now, what does this mean? But one can be somewhat more specific. Okay. So, more specifically, given any point, yeah. No, let me not say that now. This theorem can be strengthened and embellished in very important ways. And in fact, I can refer you to Ness's paper if you want embellishments of this. and connections with the Hilbert-Mumford criterion and so on. But in my view, the more I look at it, I think the moment map has really supplanted anything that you can do with the Hilbert-Mumford criterion, you can do with this and more. So I personally, so the only thing is that the Hilbert-Mumford criterion and allied things are more or less purely done in the language of algebraic groups, where you have here you have this ideas from symplectic geometry that come in, but this is much more flexible. Okay. Okay. Now, now I must introduce the very closely allied creature. So is the norm squared
So Ramadas, I have a question. So we are looking at 0 here. Could I have taken some other point and taken its inverse and done that?
So if I
get some stabilizer, some reasonable case stabilizing.
There are analogous things that you do, but you know, you have to really do the correct thing, not just random point. No.
Okay.
Yeah.
Something with some decent stabilizer if you have.
Yeah. Yeah. Okay. So now norm squared. Yeah. Let me just finish that. So M is a function from PV to K hat dual. Now choose a K invariant inner product on K hat. And in good cases, for example, if capital K is a simple Lie group, there'll essentially be only one up to a scalar. Okay. So then consider the function M squared. I'll just call it M squared PV to R, where M squared X V is MV, inner product MV. Inner product being taken in K hat. Okay, so now this is a function actually with values in R greater than or equal to 0, because you know, I've chosen an inner product. So you're taking the value of M at a point and taking the inner product of the resulting vector with itself. So the number that you get is greater than or equal to 0. So at points, it takes its minimum wherever M takes the value 0. Okay, if M takes the value 0, if M takes the value 0, if M takes M takes the value 0, which happens if there are semi-stable points at all. If PVSS is non-empty, right? Because otherwise, if this theorem tells you that if this is non-empty, the left-hand side must be non-empty. Therefore, M must take the value 0. Okay. These are the minima of the function m squared. Okay. And what the above theorem can be expressed as saying reformulation of above theorem. Reformulation. Minimum values, minima of m squared divided by k is PVSS modulo G. Take the set of minima of the function m squared and go modulo k, I get the projective quotient. Okay. Now, what about the other critical points? There are other points where this function m squared will have critical points, namely its derivative vanish. What can you say about them? So theorem, the other critical points all lie in the null cone PV non-semi-stable. Okay, and in fact, you can say more. In fact, the projectivized null cone can be partitioned into the basins of attraction of the gradient flow of m squared with respect to the Riemannian metric. Given by the Kähler form. So remember so all this, you see, everything comes from just the choice of a Hermitian inner product on V. PV gets a Kähler form. Kähler form is this wonderful package. It gives you a Riemann inner product. It gives you a symplectic structure, and they are all very intimately tied together via the complex structure. So now m squared is a real valued function, just as you use a moment map to give vector fields corresponding to the Lie algebra using the symplectic form. I can use a Riemannian metric to take the gradient of this function, m squared function. So the gradient will give you a flow on PVSS.
Correct.
But when you take the limit points of this flow, the flow will tend to points where the function has zero gradient. Many of them will be the minimum points. So those will all correspond to semi-stable points. But those guys that flow, there'll be others that will flow to non-critical points, where m squared has values, non-zero values. So just partition the whole set into basins of attraction of these higher critical points, and that this will give you a partition of the nilpotent cone. Okay, so this is the title of Ness's paper, a stratification of the nilpotent cone, and the stratification comes from this m squared function.
Okay. So once again, so you're saying so when we looked at m inverse 0, we went mod k. M inverse 0 are those nice points. Yeah.
Yeah. Those give you all that gives a semi-stable quotient.
Semi-stable points. And
M
you're
inverse
saying
of 0 consists of all m inverse of 0 consists of semi-stable points.
Yes. Okay. But also they at those points also, I mean, but I could have defined this norm square, and I could have looked at the minima of the norm squared, and you're saying they're good. There are other minima apart from these.
Not minima, critical points.
critical points apart from these. And
see, every minimum is a critical point, but not the other.
Correct.
Critical point of a function is a function where the derivatives vanish.
Correct.
Because this function is value strictly greater than or equal to 0. If it takes the value 0, it will be a critical point.
Correct. And you're saying those critical points, the value of m on that may be if they are non-zero, then they really correspond to points in the null cone. And
then you can associate to each of these critical points all the points that flow to that critical point.
Okay.
If you divide up the null cone into various basins of attraction, associated to every critical point is a so-called basin of attraction, meaning the points that flow towards it.
Okay. And that flow you are saying is determined by the Riemannian metric. The gradient of the Riemannian.
Gradient of the m squared function.
Of the m squared function with respect to the
Riemannian metric. So gradient of a function means take the function, take it d, I get a one form, use the metric to convert that one form to
a vector.
Okay. That is
correct.
I think I'm kind of breathless now, and I wanted to work out the example of the adjoint action of GLV on on n by n matrices. I don't think I have the dum or time to do it. I will, if I have I might work it, and I've mostly worked it out. I'll put it in the notes and give it to you. Okay. If you don't mind, I will stop now.
Very nice. Sure.
Sorry, I don't think I have. I can even touch upon Hilbert-Mumford.
Sure. Okay. But the moment map will be required in the next talk, so that's nice actually. At least people would. So, are there any questions for Ramadas?